All right, so this right here is going to be structure and bonding. Particularly, you can be looking at it in solids. And so this is actually a topic that should have been brought up in general chemistry. Did anybody get any of that? Unit cells, electron C. Any of this sound familiar? Okay, a little bit. Okay, so you got a little bit. So that's good. We're working from something. Always better than working from nothing, right? All right. So, right here we see examples of crystal structures. This is actually your atoms at the lattice points. Excuse me. Does everybody know what a lattice is, by the way? It's a pattern that defines the structure. Okay. Or another way of saying it, has everybody seen those lace things? That's actually a lattice work as well. Or like if you were to make a drawing of a snowflake, that would be a lattice work that you've made. You don't like shade the thing and do like fill in the parts right. You define the pattern, don't you? Okay. Okay. And so this here is another way of representing these. These are motives, okay, or motifs, depending on how artsy you want to sound. Okay. Motif is actually proper. And another way of saying this is the basis. Okay. And what it is, it's repeating patterns that define that crystal structure. Right. Now, when you're doing these motifs, you don't actually have to define specific atoms. Okay. So, for example, this one actually has the atom in the middle where you don't actually put anything, does it? Okay. And so the motif shows you the shaping that's created by it. Okay. But it can be empty space that you're defining it by, not atoms, right? Or not ions. Okay. You could define it by just one ion, so the cation only, instead of the anion and cation. Okay? You can do a lot of different things with these, and you're trying to represent the overall symmetry and structure of it, right? Has anybody ever heard tiling? Seen anything on tiling? Yeah? Like the mathematical concept tiling, or no? It's the same thing as actually like tiling. Okay, so tiling would be the two-dimensional version of this, of course, where you're fitting all the tiles together that are repeated shapes, right? That are motifs. And those repeated shapes should fill in the entire space and not leave any gaps, right? In which case, if you leave gaps, you have not successfully tiled, have you? You have done a shit job. Okay, and you should be fired. Okay. Everybody understands, like actual tiling in a bathroom or something is actually a perfect example of this. It's the same thing. But that same tiling has actually also made its way into mathematics and chemistry and sciences. Because tiling is a way you can abstract these things and figure out new patterns. Okay? Okay, and so this has a lot to do with it. You may notice it looks like tiling, right? On like a floor or something. Everybody see that okay? Okay. And so there are some basic shapes that make nice geometric tiling, aren't there? And those same basic shapes have three-dimensional equivalents. Okay? All right, so again, does this have to be an atom right there? No, no. Does this have to be empty space? No. Does this necessarily have to be an atom for all crystal structures? No, you can actually do empty space as your defining point. However, by tradition, you would define the lattice as the places where atoms would be. Okay? Okay. However, most structures, if you switch to empty space instead, you can actually replicate the same structure, of course. All right, so right here we see some examples of different types of lattices that we could generate. And you'll notice that some of these examples are successful examples, some of them are not. Okay? So we look here, A, is that symmetric? If you rotate this, is that symmetric? With a C2 it is, isn't it? Okay, but we need a C4. You should have a C4 for that. Okay? So this is not actually a proper lattice. Right? And that's because you have different defining points here and here, don't you? And so if you do one rotation of the C4, you actually end up with a different structure, don't you? And the third rotation also ends up with a different structure. So, how about that one? Yeah, repeated units that you can do a C4 rotation on here, right? Okay. How about that? So in this case, actually, if we're looking very, very closely, these are actually suitable structure right here. But you have to rotate around this. See? It goes ding, ding, ding. So you could take your tile and rotate it around within the crystal structure. And that's actually why these examples are the ones they are, is they're actually really nice examples of the different sort of motions that you would need to do for this, the different operators, right? Okay. So we're doing the different operations. So these ones are all actually proper lattices. This is the only one of these that is wrong. Okay. That is not a proper lattice. Okay, so the last thing we would always want to do here is we'd always want to have the one that has the highest symmetry and we can pack the best in. Okay. And so if we look very closely, then what would be the one that would have the highest symmetry and would give us the best packing within this? And you already came up with it. Yeah, this one right here, right? Yeah. The rest of these actually give us lower order symmetries, don't they? Mm-hmm.
You still rotating them like that, just like center rotation.
Yeah, because you're doing it for a crystal. Yeah. Not necessarily this one itself. Yeah. So it's the symmetry of the crystal that matters. The same thing here, that's why this one can function, is because you can rotate it like this, right? The whole structure. And so again, think of these as tiles. Could you successfully make patterns out of those tiles that would be repeated, symmetric patterns? And this is the only one you couldn't because of this. These are different right here. Once you start tiling it out, you won't be able to make patterns. Okay, so this is the one of the ways you can actually determine your external symmetry of this crystal. And so what we do is we actually draw perpendicular lines that would go out to the face of it. And then you would want this fourfold rotational axis within this symmetry. Okay. And remember that this extends out. And so you would look at whether the numbers of atoms within match. Okay. And so this would actually give you a fourfold symmetry overall. And you can actually see our structure right there is what our best pattern actually is. All right. So one of the things I need to mention, and your book is okay. So I do actually have a question for you guys. That's also a different thing as well. And this is kind of a question on who here needs to take instrumental chemistry next. Okay. No. Did you already take instrumental? No. Okay. Okay. Advanced biochem. Yeah. You gonna take advanced biochem or instrumental? Advanced biochem. Okay. Okay. So instrumental, would you guys prefer a more in-depth book or an easier to understand, not so dry book? Okay. Okay. The other one is a lot more in depth and has a lot more use outside of here. Yeah. If I had a 2-book system, would you guys kill me? Okay. I'm gonna have to think about it. Yeah. Luckily, we got a year, right? So we got a semester in between. Okay. So this book we're working from right now, and I gave you as your textbook, is a pretty nice in-depth book. It has pretty reasonable explanations. It's not super dry. But one of the things it does assume is that you actually did have a good general chemistry. And you know some of that information. So, this right here is a primitive unit cell. This would be a non-primitive unit cell, okay? This is it could be several different things. This is probably a either face-centered or body-centered. Since we're looking down, we can't really tell, okay? But we'll get to the next ones in just a bit. So primitive unit cells don't have anything but the vertices defined. See that? So the atoms or ions or whatever we're using as the thing that's our vertices is centered on the vertices. And that's the only place they're centered. So for in 3 dimensions, this is what a primitive cell would look like. See how all the vertices, are defined by our atoms there, right? Okay. And so that is primitive because we have more complex structures that could be possible, right? So this is body centered right here. And see how there's one in the body center? Yeah. And so body centered is there's one in the center of it. This is not primitive. Yes. So this is not one of the primitive ones. This also is sometimes called simple unit cell. But primitive is by far and away the one I've seen the most. This is face centered. And so what you'll see is the center of each face has an atom in it. Those would be half in, half out. Anybody remember any of this? Okay, fair enough. So these ones right here, they would only be a quarter in now, right? The one in the center obviously is completely inside. And then this one is only half inside, right? And it's shared with the other unit cell on the other side. So for example, that would be that one for the next one, right? Okay, this right here is another example of a face-centered. That's another way you could have a face-centered. And this is actually a rhombohedral right here. You notice it's not a simple square, right? Mm-hmm. No. No, it's not primitive because it's not the simple square sort of shape or rectangle. Doesn't necessarily be a square. So that has a separate definition. Okay, so this right here, I want to clarify and make sure that we remember something because it's going to become a little bit important in a bit. So if we look at symmetry operations and symmetry elements, okay? So symmetry elements are the elements that make up operations, right? So for example, you have symmetry elements like a reflections, rotation, right? Those would be 2 different symmetry elements. But if you did an improper rotation, notice that uses those 2 elements, doesn't it? And so that would actually be an operation, okay? Where you operate those elements. You do a set of symmetry elements that give you the operation. Okay, so let's talk about another type of symmetry operation. These were things that we ignored before because we were doing individual molecules and atoms and stuff, right? But so when we were doing them before, we could move them around in space and it didn't have any effect on our operations or elements, did it? Not particularly. Like, just doesn't have any effect on the molecule itself, does it? Okay. But when we're looking at something like a crystal, right? That would very much have an effect, wouldn't it? Okay. So for example, if we had this right here and suddenly we move this atom, what would happen? That would affect our symmetry, right? Yeah. And so when you're looking at things like, anybody ever seen like the old quartz Hertz? crystals for the radios and stuff. Okay, so that's how radios used to work. You take a piece of quartz usually, and what happens is the radio waves cause it to vibrate. Okay, those vibrations would actually be translations within the crystal, right? That would cause different levels of vibrations depending on the radio signal. Okay, and so you'd tune in to a station. It would be a specific frequency set, and then you would have that pulse radio waves that causes the quartz crystal to vibrate, and then you put some sort of sensor that causes it to give you sound. Okay, all right. You can actually make it as simple as literally the vibration basically is just hitting something and that gives you literally the sound. Okay, you can actually do that with an antenna, by the way. Anybody ever seen one of those before? So it's actually kind of funny if you put something that interferes with the antenna, and brings it down into audible range, of course, instead of electromagnetic range. Something like a pickle. You can actually take a pickle, touch an antenna with it, and you can actually hear the sound from the station coming off it. And that's because as long as you put something that its vibrations are caused by the frequencies coming off of it, right? You're going to be able to hear it. Okay? You can also see the sound too, but that's not helpful. Because most of us don't see sound, right? All right, so those are our symmetry operations and elements. And so the new ones we have to think about right here are going to be things like glide planes and screw. So this right here is a glide plane. This is G glide plane, where it's just going across axially. And so what you'll see here is this would actually be that T distance here. That would be your unit cell distance. Okay? So that would be the measurement of your T here. All right. Your unit cell. So one end of your unit cell together. Okay. And so if you move half of T through your unit cell, what you'll see, and then do a reflection, what you would see then is you would actually end up with that reflection reflecting across, right? And so, for example, this is one of the reasons why this one doesn't work, does it? If you go half of this and try to reflect across, that is not okay, is it? It's not a reflection anymore, is it? Okay, you go here and we go halfway across. We get a reflection, don't we? So right there. And that gives us a reflection, doesn't it? And we do the other ones and we'd actually see reflections. And it'd reflect, right? Okay. So it would be here. Let's try this one. Okay. So imagine a plane, right? So we got this plane right here. Imagine that plane goes halfway through here. So now it's there, right? Okay, so then you do a reflection operation, right? And those would all match, wouldn't they? Okay. And so that has a glide plane symmetry. It has the axial glide plane symmetry, or G glide plane symmetry. Okay. Okay, this is another type of glide plane symmetry. And so in this case right here, this is going to be that diagonal one. And it's where the glide plane moves diagonally. Okay. And so what you're going to see is it's going to translate half of A and then half of B. Okay. And so that would be half of A and then half of B. And then you would do a reflection. Okay. Mm-hmm. Mm-hmm. It can be, yeah. And so the next one we're going to do here this is going to be a diamond. This is actually named after a substance. So has anybody ever seen the lattice of a diamond? No? Oh, that's just disappointing and sad. Okay. So diamond lattices, diamonds are tetrahedral, right? In their geometry. So if you had covalent bonds between a bunch of carbons, they'd all be tetrahedral, right? And so what you end up with is just repeated units of tetrahedral coming out. And that's a diamond lattice network. Okay? It's called a molecular network because it's molecular, right? Not metal, not ionic. Okay? Okay, so this one's defined by diamond, and it's called diamond literally because it is what happens in diamonds. And that's like the representative example. Okay, so it's essentially a tetrahedral sort of reflection. Okay, and that's, you see the 4 here. That's why the 4, right? Is because tetrahedral, 4 around, equally spaced, right? Yeah. And so what you'll see here is we can move it by a quarter instead of a half, right? It's very similar to diagonal, but instead we can only move it by a quarter and we'll still get a reflection. And that's because the high symmetry level that tetrahedral gives us, right? Okay, so let's go ahead and look at a glide plane done in a 3D model real quick, okay? I need to install this on this computer. I didn't realize I didn't have it installed until this morning. I had to throw these on. I was going to try to get it installed during my exam, but I got a bunch of questions. So, okay. Anyways, this program's actually free. You just have to request to download install, and I had it on my previous account, not this one. So this right here is actually a glide plane shown in maleic acid. This is actually the C glide plane. And you'll see here that we've moved half of the distance, right? Everybody see it okay? Okay. Again, the exact molecules, how they line up in this, doesn't actually matter. Okay? You just have to align your vertices in such a way that you get repeated units that would go through this crystal, right? Kind of like your tiles, where exactly your tile is your bathroom floor starting, doesn't exactly matter, right? We just have to get tiling that goes out repeatedly, forming a symmetric pattern, right? Yeah. Okay. And so this would be the glide plane right here, where we'd move it half down, then we do a reflection. Okay. Okay. So this right here is actually a screw axis. And so this one actually shows you several screw axes. And what they're going to be is they're going to be like C rotations. Okay? Just 3-dimensional C rotations in a crystal. All right? So literally you're going to go down. Okay? So like think of it as a rotation, but you're moving it like a screw. You know how screws go. Okay? Okay. And that's going to allow you to do your rotational within a 3-dimensional structure like a lattice, right? Because you have that extra element of being able to move down. Okay? Okay. And so again, these are not elements, right? The elements are things like rotations, aren't they? Reflections. Okay? So this would be, for example, a translation plus a reflection in our previous material we've done, chapter 6. This, though, is the operation called glide plane, right? So glide plane, translation, plus reflection, right? Yeah. The elements, again, would be translation, and then a reflection, right? And E because everything has E. Identity. Yeah. But, okay, so this again is going to be 5 different examples of different screw axes that you could do. And so, for example, right here, we have our axis. And this would be that kind of simple screw axis that you probably were thinking about when I said screw, right? So it's done, then done, then done. Just down, right? Yeah. Yeah. And so this would be a slightly more complex one. This is more like a bolt or something, right? Where it just goes, of course, when you go down, it matches that one, it matches that one, right? But this one also matches that one, so that still works. Okay. And so again, this one's probably what you is kind of an interesting one because it's like a C3, isn't it? Can everybody see that? It's just repeated C3s, isn't it? Yeah. But you can also do a 3 rotational axis with only one thing on it, right? Because you can move down each step instead of having to do it in place. Okay? Because again, this is the operation, which includes a translation, right? So we move down and rotate it 1/3, right? And that matches. We move down, rotate it 1/3, that matches. We move it down, rotate a 1/3, that matches. Okay? I'm honestly unsure which one actually is more helpful in terms of figures. If I'm being really honest here. Can you guys see that this one is just rotating like that, right?
See the other one, but that is good.
Yeah.
Together.
Okay. Yeah. So anyways, there's that, right? Okay. And that's your C2s here. And you can see the terminology here, 2-1 right there. So that's the 2-1 right there. Okay. All right. So a two-dimensional lattice represents how only the values of Cn are consistent with the generation of a second row of the lattice points. So when we do these operations, what you're going to notice is there's actually a very limited set of C rotational axes that will work for this. Okay? And that's because of the limits of the molecule. Right? So for example, is there infinite space to move downwards? No, there isn't, is there? Has anybody ever seen like a 5 element around that matches nicely and doesn't have to have something else filling in for it? Like anybody ever seen stars that are repeated stars that match nicely? They have C5, right? No, you haven't, have you? Like they do put them in tile systems, but they have to cut it out, don't they? Yeah. They don't match. And so the possible C states that you can be in are actually only these ones right here. Any other rotational axis for these will not give you all filled space. And so we're not unit cells that will work. Okay? They're simply not symmetry operations that can exist in a crystal system. Right? And that's again because you have that 3-dimensional lattice. Okay? Okay. And so what we see here is it's 1, 2, 3, 4. 5 got skipped. Then 6. And you can't actually have higher. Okay. And we can actually see here, if we look at these structures right here, this is the tiling of that. Okay. 3 works great, doesn't it? Okay. 6 also worked great. Actually, you knew that because 3 works great. Can everybody see the 6 in here? This right here is a C6 right here. Yeah. Yeah. So hexagons and triangles are actually, hexagons are just a bunch of triangles, right? All pointed in. Okay. Anyways, this would be your 3, 4, then we get our 6, right? Okay. It doesn't really make sense to try to tile the lower symmetry structures. Though, did you guys know that they actually found unsymmetric structures that can tile now? It's a whole thing in mathematics. No? Yeah. So they've actually found a single and a set of unsymmetric structures you can tile with that have no symmetry internally. Yeah. And will make unsymmetric patterns the entire way out. Yeah. So it could actually be really interesting for some like quasi crystal materials, and we'll talk a little about that. But yeah. Look at 5 real quick. You can't do the 5, can you? Yeah, you can't actually make unit cells with that. You'd end up with empty space, and so that actually doesn't work. 8 as well. You can see you'd always end up with empty space, and so you can't actually tile successfully with those. Okay. You'll see if you ever look at going to a bathroom, by the way, that has 5 or 8, they have another tile that's a different color that they put in. And they do make repeated patterns of that empty space, but you have to have a 2-tile system. Okay. All right. So this again is that same thing we looked at before. This is actually your cubics right here. So that's simple or primitive, right? And that's your cubics because they are equal distance on every side, right? So a cube. This one's the face-centered, this one's the body-centered. You'll notice the previous figure I didn't differentiate because I just wanted to introduce simple or primitive, right? Okay, this is monoclinic. And so you'll see that you have 2 sides that are the same, right? And so this one here is the simple or primitive. This one here is end-centered. You actually have another, you can't be completely face-centered where it's on all the faces, right? It has to be end-centered instead because they're not the same facing, right? On every side. Okay, this one right here is orthorhombic. This is actually where you'd, okay, the previous one had rhombohedral in it, right? Not orthorhombic. Where you'd ask me about primitive. So, yeah, let me go back on that. I don't remember if my previous one was that. Shit, it was. Okay, sorry about that. I only glanced at it. I didn't look very carefully. Yes, you can be primitive. Okay? And that one is actually primitive. All right, so orthorhombic, this is simple or primitive. This is your face-centered for orthorhombic. Remember that they are similar, but they will not be 90 degrees in orthorhombic, right? Not 90-degree angles. This one's body-centered right here, and this one is going to be rhombohedral. This is where the sides are not the same on both. So you only have 2 sides the same, not all 4, right? And this is going to be end-centered. This will be your simple. This right here is going to be tetragonal. And that's your simple and body-centered. Hexagonal, this being your simple, and triclinic. Notice that triclinic, you actually have one position that'll be missing that atom. Okay. Everybody see that, okay? Okay. And that's why it's called triclinic, right? Tri 3. All right, so these are actually your 7 crystal systems. We've organized them here into edge lengths and bond angles. This is the crystal system here. Those are those ones that were up here. Okay. This right here would be your Bravus lattices. This is your edge lengths. Notice cubic, all your edge lengths are the same. This right here is how you define your XYZ system within a lattice system. Okay, so for reasons, specifically because your XYZ of your molecule can be different than your XYZ of your lattice system, right? They do not use XYZ for the lattice systems because it gets confusing then. So remember that you could have a different molecular geometry than you would have as a lattice geometry. Okay? And so your axis systems and molecular geometry was always what again? Your highest rotational axis, right? Okay. And that was your Z. And in this case, this in a lattice system, that may not be the same Z. And so instead is done as A, B, C. Okay? That's actually, did I have my ABC here? No, I did not. Damn. Okay, that would have been helpful. All right. So this right here is your defined angles, and notice again the hexagonal and rhombohedral do not have 90 degrees for everything. Okay. These are actually the allowed point groups within that. And so you see here that, for example, these can be extremely high levels of symmetry. Okay. And in fact, cubic really don't go low symmetry, do they? Because by definition, cubes have to have pretty high symmetry. Okay. On the other hand, once you start getting up to here, your symmetry falls off pretty rapidly. So, for example, the monoclinic, the symmetry actually falls off extraordinarily fast because, again, you have that unsymmetric ends, right? Okay. So those are your allowed symmetries. And those are those same allowed point groups with that same set of elements and operators that we had looked at before in chapter 6. All right, so this right here is going to be your different diagrams that show your face-centered here. And so this is a face-centered tetragonal unit cell. And then if we look here, it would actually be very equivalent. It would be equivalent to a smaller body-centered tetragonal unit right here. This would actually be your top-down view. And so right here, we see the face-centered one. Over here, we see this one from the top down. Can everybody see those okay?
The one in the middle is representing smaller body centered.
It's both.
Oh, okay.
So this one is this one. Okay. This one is that one. Yeah. So putting these together, you can get a crystal structure, but you'd also generate these smaller body-centered ones as well. Okay. All right. So again, we have here the three Baravis lattices in our cubic crystal system. This would be the simple right there. This one right here would be your body-centered, and this one right here would be your face-centered. Okay. Everybody okay with that so far? Yeah. Is this starting to look more similar at all? Okay. Okay. That's fine. So let's talk a bit about the relationships between the three different cubic unit cells here. So the simple cell is going to have one at each point, right? But remember that one of these atoms is not fully in it, is it? So a simple unit cell only has a portion of it in it. Okay. And so altogether, that's 8 of them. Each of them would contribute 1/8, right? Because they would have 4 and then another 4 below it, splitting it. Okay. And so altogether, we get 1 atom per cell, don't we? Okay. All right. So our coordination number would actually be 6. How many sides does a cube have? 6 in this case, right? Or how many things is surrounding it? Each one? 6. So our coordination number ends up being 6. That's how many things can actually coordinate with it, right? Remember our ligands and coordination? Okay. All right. And so we go on to packing efficiency. And what we see is the packing efficiency, if you were to tightly pack this as much as possible, is actually only 52%. Okay. And so we would end up with about 48% empty space, 52% efficiency. If you were to take geometry and try to figure out your radius relationship between these things, what you would notice is your A here would give you your radius between them if you divide it by 2. Right? And that's because they're just on the vertices, see? So literally, if you take this distance here, divide it by 2, that gives you the radius of each, doesn't it? Everybody said okay? All right, so this right here is your body-centered. By the way, these right here are the abbreviations. If you start actually doing this and using this consistently, you would end up saying the abbreviations all the time because these are very long, right? And so SC, BCC, FCC. All right, so let's look at the next one. The body-centered has the same as this, but one in the middle, right? And so you got two atoms per. The coordination number is going to be 8 because we can have more of these around here coordinating to any one of these, right? And so we get a coordination number of 8. Okay? Remember, these would be repeating around on each side. Okay, and so our packing efficiency is going to be 68%. We can pack more efficiently in this case. And our radius relationship is going to be slightly more complex, isn't it? Okay. So what's going to end up happening is if we were to see these as space filling models, not points, right? So space filling. What you would see is this one only goes like that, right? It doesn't go all the way to the half, does it? And that's because this one would push those all out, doesn't it? Okay. And so we actually have to do triangular calculations like you would do in geometry, right? Trying to find like the distance, the radius of two circles that's within a sphere, right? Or in this case, a cube. Okay. And so what you would actually find if you go ahead and do those calculations is if you take the square root of 3 times a, so a again is what? Anybody? Huh? Is the distance here. Yeah. In this case, because we're cubic, it's the distance on any side, right? Yeah. They're all the same. They're all a. Okay. And so what you would then do is you would divide that by 4, and that would actually give you the radius of any one of those atoms there. Okay. Okay. Keep in mind, do these need to be, say we're doing this for NaCl. Does this need to be NaCl over here? No. In fact, it probably is not. Okay. Most likely it would be for one of those, chloride or sodium. And so these would all be sodiums, and then the chlorides would be like that. And they'd just be diagonal tone, offset. It depends on how you define your pattern within your crystal. So for example, some crystals, it's actually better to define them off of the empty space because they have very high symmetry, and it'd be very difficult to define this cube, right? More often than not, what you'll see, especially for ionic solids, is that they'll be defined based off of either the anion or cation. Usually the anion and cation are actually just an offset pattern. But if you get more of one versus the other, you're going to see a difference. You can do this for minerals, and this is one of the major reasons it's like that, is because for minerals, have you guys ever seen a chemical formula for like a mineral? No? Okay, so minerals actually are a lot more complex, and they have little formulas for the chemical formula. Okay, so you'll have this deal where it could be the metal could be strontium, potassium. It could be a bunch of metals that all have about the same size. And then it could be all a bunch of different anions that all have about the same size. Usually it's the metals, though, because there's a lot of metals that are pretty similar size because one has a larger charge than the other, right? Okay. And so what ends up happening is you end up with this equation where you have X of those minus Y of these. And that gives you your number of metal ions. And they can be swapped out. And you still want a crystal structure because they have the same size. They can be swapped out. And so you end up with, these could be like potassium strontiums right here. Okay. Same size, different element, right? And that's one of the major reasons that this is actually made, of course, largely to do things like minerals and stuff, right? Um, and that's a very common problem. Okay. And it doesn't really matter for the crystal structure. You'd still get the same overall crystal structure. It's called doping. You can do it with processors. You can do it with crystals. You can do it with all sorts of things. And that's why you get like the different colors of diamonds or rubies or is that's actually that where it has different metal ions that are being doped in.
Center body center.
Mhm.
That taking up more space than the other vertices.
Nope. Nope.
Not
They all
just-
take
they're
up the
all
same
evenly
space.
spaced out.
Yeah. Yeah. In this case, all the empty space is right there, right? In the middle. And in this case, it's going to have empty space over here on the sidewalls because this one gets put in the middle. It's still more efficient packing, but it shifted that empty space out and it makes the math to figure out the radius a little more complex, right? Because they can't touch each other anymore. Yeah. 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 Which is annoying, but it is, right? Gotta deal with the world as it is. All right. So this one's the face centered. And so remember, these are going to be on the faces here. And so they're half in, half out, right? They're shared between the two unit cells. Okay. And so you'd have half, 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 half. When we add them all together, we get 4. So there's 4 atoms per cell. This is going to have a coordination number of 12 because we have a lot more of these that are actually next to each other in this arrangement, don't we? And you can see that fairly easy, can't you? Yeah. And so the number of these that could be coordinated to each other would be 12. Okay. Okay. Now, the radius, packing efficiency 74%. The radius relationship is going to be the radius equals square root of 2 times A. Again, that's that sidewall, that distance. And then that's going to be divided by 4. And again, you notice that's that same triangular relationship that you would have used back in like geometry. I know it's been a long time for geometry. Do you know I actually did way worse on my ACT because of that? I had taken geometry at the end of elementary school. And then they had no calculus on the ACT. Really pissed me off. Damn it. Okay. How are we doing for time? I am running out of time and I really okay. This is an example from your book. I'm gonna use this as the example at the beginning of next class period, okay? Okay, so go ahead and work it a bit. It's a little long for an example as a class period thing. And this is actually a problem that I used to give in Gen Chem as well. So it's actually not a very difficult problem if you know the trick. Okay. All right, so let's talk a bit more about closest packing of spheres. The PowerPoint is up online, by the way, or example 8.1 in your book. Please don't look at how you solve it, though. Like, do it first. Then you can look at how you solve it. Okay, so the closest packing of spheres, this is going to be here. We're going to see the first layer, okay? So we have spheres, and the best model in your mind here is actually, has everybody picked up balls at like the end of an activity and had to put them in a rack? Okay, that's actually a great model in your mind. Or when you're a kid, you picked up your toys and had to like stack them, right? And you had to like fill space and stack them right, or else you couldn't close the lid, right? Okay, same thing here. We're trying to stack our toys, in this case atoms, right? And we're trying to stack them so we can close the lid on. Okay, all right. So right here we have our different unit cells, and you can see you can actually make various different unit cells out of this, right? Can everybody see that? Okay. Okay, and so what we're going to do here is we're going to put these so we can stack them up with the closest possible stacking relationship. And so this is the next one. And how you would think of putting these together is you'd have one layer, We'll call that A for this one, okay? But it could be A, B, 1, 2. We would have one layer, right? The next layer, you're going to put the balls where? On top of the previous ball? No, in the middle between them, right? So there's little triangles around them, right? Okay. And so we offset so it's in that empty space, right? So we can get them closer packed. Okay. And so that's the pattern you're seeing here, right? Okay. Everybody good with that so far? Now, there's actually some different patterns that can develop once you get a third layer. And so once we put the third layer, there's a couple of different options, aren't there? Remember, this extends out, doesn't it? Okay? This extends out into space. So we can put it one over again, right? But we could also go the other way, couldn't we? And that's actually going to give a slightly different stacking pattern. Okay? Okay, so again, these are top down. Let's go ahead and rotate it so we can try to see these toward the side. Okay, it makes a little bit more sense. So A here, that was that A one. This is actually called HCP, which is hexagonal close packed. Okay, and you'll notice that it actually makes a hexagonal shape here, which is what that's named after. Right. And so what you see here is we have layers. We have our A here, and then we'd have B, which is going into these pockets right here, right? Everybody say okay? And then we'd have A again, and then B again. And we just keep going back and forth until we're done. Okay? And that's probably the one you thought of. It's did anybody think of a different pattern than just repeats of the same? No? That's fine. That's very much a normal thing. People like symmetry, right? So if you can make two that do it, why make three? Okay? However, there is another way you can do this, and that is that instead of having them like this, you rotate, right? Yeah. So what we end up doing is we do a third rotation each time. Okay? So you get your A right here. Again, that would be your A. And then you fill in the space in between, right? Okay. And then you put an A on top of that. And so each time we're just rotating up. Everybody see that? Kind of like our screw symmetry, right? Hey. And so you're just rotating each time. Okay. And so you end up with 3 because it's rotational axis 3, right? A, B, C. That making sense?
Are these the same like efficiency for packing?
You know what? I do not remember. If I remember correctly, this is cubic close packed. I'd have to look it up. It's probably listed in your book if I remember correctly, but I want to say this one is actually slightly more efficient, but I don't think it makes a lot of difference if I remember correctly. Okay. It depends on what you're packing in these. But if all items are the same, there is one that's slightly more efficient. I just forget. Yeah. Okay. So, good question. I can look it up sometime if you remind me to look it up.
I think you said both are equally efficient.
Okay. Yeah, so if they're even, then they're equally efficient. Okay. This actually depends right here, which one you get. Actually depends on what your items in here are. So if you change the items that they're defining these, you're going to change the efficiency, and it packs the more efficient way. And then that's why you get different structures. I'd have to look that up again. Yeah, thank you for. Okay, this right here is then your HCP, and this is the other one right here, the cubic, and you can actually see the cubic actually makes a nice cubic pattern here with symmetry. whereas the HCP right here actually makes a hexagon pattern right there, right? You can do it as 4-itemed squares sort of things. This right here would be your 4-item. That's your face centered right there. Okay. This right here would be how you can do that over and over. Okay. And so we got our stacking right there. All right. I'm only going to put a very small part of this table in here because you just do not need all this table in here for me to talk about it. It's quite long. It's 32 items long. And I'm definitely not listing the 230. I'll tell you that right now. Okay. Okay. So there are 32 crystallographic point groups that will be combined with different lattice translations, i.e. those screw axes and glide planes. If you then remove all the degenerate redundant results, there's actually 230 possible combinations, and these are your space groups. Okay. Okay. And so these are the 32 right here. This is the Schoenfly system. Everybody remember your Schoenfly system? That's chapter 6 system. Those are your point groups. Okay. And then this is the Hermann Mulligan designation. This would be your crystal system right here. So this one would be triclinic. And that's just a stereographic projection, so you can see how they would move around. Okay. Okay, so remember, this is before we start adding our new symmetry operations, right? If we add our new symmetry operations, we get up to 230 unique ones. Okay. Okay. So this actually has a tabulation. So if we look at the tabulation of these 231s, this is the International Tables of Crystallography. And then you can look in, and it actually has these symmetries and how they operate. There's actually nice ones now online, and I've actually put that on. I guess let's stop here, and can you guys give me a minute, and I can talk about the. Okay. So select mine. Oh God, you guys see my calendar. Yeah, there's a problem here. All right. So we go to Canvas real quick, and we go. Can everybody get to your canvases? Okay. So if we look at the class here, I went ahead and just put all the materials into a web page for useful information. It's under Pages, under your Canvas. Okay. You may want to go ahead and bookmark some of these things that you might think is useful. I'll probably be adding to them as I get some time, but it's something I've been meaning to do, but I'm just having a lot of trouble finding time to do it. Okay. So this right here is the inorganic one. There's also things like that give you my videos for organic chemistry and all sorts of stuff. So this right here is actually a really cool, like, oops. Now, unfortunately, this is breaking because the person that used to update this is no longer updating it properly for the new web. But this has a bunch of different isotopes and their information, in case you're ever curious. This right here is actually a 3-dimensional examples of symmetry groups. Some of you have actually seen me use this. And so right here is point groups, and we can go here. You will notice some of these are actually crystal structures. In fact, some of the ones I had put on the exams were crystal structures. See that? Yeah, a lot of these were actually crystal structures. Especially the higher order stuff. A lot of the higher order stuff is crystal structures. Harder to make them. You have to put a bond in between, right? All right. And this actually has a nice thing where you can actually see the rotational axes, and there's your S4 operations. Okay. Okay. And so that's just an interesting little piece of information. There's a link to it and you can use it to see what different sort of symmetries would look like. Okay, you can use it to practice, in fact, if you ever have any more issues with figuring out your symmetry elements and operations. So this is the crystallographic information. This actually has all the different information that we'll be going over. And so, for example, we can go right here, and we can see the different symmetries. And that's the crystallographic information, and that would actually be what it would be in matrix form. And those would be your symmetry operations. Okay. You can actually come an interesting thing. Okay. These are some other textbooks for different courses that are actually kind of nice for different things that I went ahead and added in here, okay? I'll also be putting some more sites. There's actually some like organic chemistry sites that are very useful. If you ever get out into careers and need that, that's right. Watch out for spectroscopic tables from Colorado Boulder.
It's the first one that comes up too.
I know. And there's quite a few wrong on it. Yeah. UCLA is excellent.